Hi, welcome back to AP Chemistry with Mrs. Mays. This podcast will focus on ultraviolet and visible light spectroscopy. First of all, ultraviolet and visible light is, of course, using the rainbow colors and ultraviolet radiation. These are going to be more energetic than infrared radiation, and therefore they would have a higher frequency than the infrared. The visible light portion is in a very narrow range. The light that we can see is in the wavelength of about 400 to 700 nanometers. That's all that we can see. Our eyes don't detect ultraviolet wavelengths that range from about 10 to 400 nanometers. So UV-Vis, ultraviolet and visible light wavelengths, affect the most weakly held electrons, typically our valence electrons. And it can cause electrons to transition or to move from one energy level to another, not completely leaving the atom, just moving around in energy levels. And because of this, it may also affect its chemical bonding. This picture gives us an idea of which energies are causing which transitions. So big energy makes a big transition. And that's why the blue light is shown for going in a longer leap than the red light, because red light contains less energy than blue light. So you'll see this in the flame test that we do for the atomic emission spectrum. Compounds that are containing transition metals that have partially filled d orbitals are the most colorful compounds, and they're most suitable for visible light spectroscopy. Things that are brightly colored are better for light we can see. That makes sense. There are many other excitations that are not associated with colors, but rather with ultraviolet light. So we have to use other detectors besides our eyes to get to those. UV-Vis spectroscopy is most common in the quantitative analysis of solutions. Quantitative spelling here. Through the application of Beer's law, where we can equate through the graph of a straight line the absorbance of a substance and its molar concentration. So we did this in our first lab of the year with the concentration of food dye and the concentration of copper in brass. Here's an example though. As the color of the solution fades, either because of a reaction or from diluting our solution, then the absorbance decreases. And we can measure the amount of absorbance that's remaining at any point in time, like comparing 2-minute solutions to a 5-minute solution, or we can create a series of dilutions and figure out the concentration of any sample at any given time. So UV-Vis spectroscopy may not be the most energetic type of spectroscopy, but it's certainly got useful applications.